Hello everyone. Today I am going to take a video's theorem of Rank Nullity Theorem. I have already uploaded the only statement part. Now we are going to see the proof of this theorem. So once again we will revise what is a Rank Nullity Theorem. So for that we are taking two finite dimensional vector spaces and one linear transformation T from V U to V. Then we have to prove that dimension of domain, that is our U, is equal to dimension of kernel of T plus dimension of image of T. This is called kernel of T is also called as a nullity of T, and the image of T is also called as a rank of T. That's why we will prove that dimension of U is same as nullity of T plus kernel of T. Now we are going to see the proof of this statement. So we know U and V are finite dimensional vector spaces. So first of all we will assume the dimension of U as n and dimension of V as a m. Now we know that the kernel of T is a subspace of our domain, that is our U, and U is a finite dimensional vector space. So that's why our kernel of T is also a finite dimensional vector space. Now we will assume that the dimension of kernel of T is k. So once we know the dimension of our kernel is k, so we will assume the basis for this kernel of T is u1, u2 up to uk. Now we will extend these k bases to the basis of u, because we know the dimension of u is n and dimension of kernel of T we are assuming k, and k must be less than or equal to n. That's why we can extend this basis to a n. Now we will assume the basis of u, our domain, is u1, u2 up to un, because u is an of n dimensional vector space. Now if you are taking a linear transformation, so any element from our domain u will be mapping to the element of V, which is our codomain. So our U1 will map to T of U1, U2 will map to T of U2, UK will map to some T of UK, and so on. UN must be mapping to T of UN. So all these elements are nothing but the subset of our codomain, which is V. Now we know the dimension of our domain is n and dimension of the codomain is k. So now we are going to prove the dimension of our image of T is nothing but n minus k. So for that we will show that T of uk plus 1, T of uk plus 2, and so on, T of un is nothing but the basis of our image of T. So to prove that this set is the basis, so we will assume this set as a S. Now we will show that this set S is a linear span of image of T, and it is a linearly independent set. So to show that this element, this S, the spanning the image of T, we will take any element of our image and will show that these element can be written as a linear combination of element of S. So we will assume V is any element of image of T. So we know that there exists some element in our codomain such that element mapping to the V. Now we know our domain U has a basis U1, U2 up to UN. So any element which is in our set U can be written as a linear combination of this U1, U2 up to UN. That is means linear combination of a basis element. So we can express our U as a C1 U1 plus C2 U2 and so on Cn UN. Now if we apply the linear transformation to U, so that can be written as T of C1 U1 plus C2 U2 and so on Cn Un. Now we know that T is a linear transformation, so we can take constant out and the linear combination can be splitted. So this transformation can become C1 T1 of U1 plus C2 T of U2 and so on Cn T of Un. Now we know this U1, U2 up to UK, these all elements are nothing but the element of our kernel of T. So hence T of U1, T of U2 till T of UK, all the things become 0. So now the remaining elements are Ck plus 1 T of UK plus 1 plus Ck plus 2 T of UK plus 2 and so on Cn T of Un. So our V can be written as a linear combination of T of UK plus 1, T of UK plus 2 and so on T of Un. That means what? The linear span of S spanning the image of T. Now the turn is to prove that S is linearly independent. So how to prove the linearly independent? This linear combination of T of Ui is equals to 0 such that the each of one of the coefficient has to be the 0. So we have to take C or I is equals to K plus 1. Here the correction is there. K plus 1 to N is equals to 0. K plus 1, or we can take I is equals to 1 to N. I is equals to 1 to N. It's okay. K plus 1 to N is equals to 0. Now we know this Ci can be, we can take inside the T of Ui. So we can write down this one as a T of I is equals to K plus 1 to N Ci Ui is equals to 0. Now Ck plus 1 Un is equals to 0. Now we can add and subtract this one as a